Good afternoon, everyone, and welcome to today's session of Al-Khwarizmi Applied Mathematics webinar. It is a great honor and a pleasure to introduce our guest speaker for today, Dr. Abdessatar Souissi. Dr. Souissi is a former student of the prestigious École Normale Supérieure in Tunis and held the position of agrégé de mathématiques at IPEST Marsa, University of Carthage. Since September 2018, he has been serving as an associate professor at Qasim University in Saudi Arabia, while maintaining his academic contributions at the Preparatory Institute for Engineering Studies in Monastir, Tunisia. Dr. Souissi is a distinguished researcher whose work lies at the intersection of quantum information and mathematical physics. His expertise spans the quantum Markov chains and the fields on graphs, with profound applications in quantum statistical physics and hidden quantum Markov models. Today, he will lead us into a fascinating area of his recent research. The title of his talk is Ergodic Theory of Inhomogeneous Quantum Processes. This topic is of particular importance as it explores the long-term behavior and stability of quantum systems that evolve under changing conditions, a field where Dr. Souissi has made significant contributions. We are very fortunate to have him with us to share his insights. Please join me in giving a warm welcome to Dr. Abdessatar Souissi. Doctor, the floor is yours. The floor is yours.
Thank you very much, Dr. Rafiq, for this nice webinar that you are organizing since years, and it becomes a really nice tradition, and for having me in this webinar for the second time. Actually, it's a great pleasure to present my work within this webinar. Okay, today's work concerns an ergodic theory for inhomogeneous quantum processes. Indeed, since the audience is mainly general, I just wanted to start with a small historical motivation about the ergodic theory. Indeed, it starts with the Boltzmann vision that says historically that the ergodic average or the microscopic time average coincide with the ensemble average regardless of the trajectory. Like given any arbitrary state of the system X, this limit converges to the expectation value here. It was introduced with a deterministic framework, and such a conjecture, it presents some limitations. And later on, Paul Erfest and his wife, Tatiana Universus, they presented somehow a model that shows the limitation of the Boltzmann approach by considering an experiment that in which we have a gas between two urns, and the point is that giving a big number of particles within a time, the number of particles in the urn A becomes like completely unknown. Like the information becomes very, very unknown. Like it can be studied as a Markov chain. Indeed, if we take xn is the number of particles in the urn A at time n, we can easily approximate this model with like a time homogeneous Markov chain, and we show that the unique invariant distribution is the binomial Bn 1/2, and asymptotically when n goes to infinity, we can see that xn divided by n converges almost surely to 1/2. It means that it becomes like a reversible phenomena, because we somehow the number of particles is like divided into two parts quantitatively, and it shows that probabilistic approach should be put on the Boltzmann is vision, or the Boltzmann hypothesis. And here we speak of almost sure convergence. Then the ergodic theory have been developed through the von Neumann mean ergodic theorem, also the Birkhoff pointwise ergodic theorem, then a lot of development within the mathematical theories, such as the Kolmogorov-Sine entropy and also abstract unknowable groups operation and non-commutative ergodic theory, and also within the classical quantum probabilistic framework. And what we are interested in here is the application of this ergodic theory to the, precisely the non-commutative ergodic theory to the quantum information process. In quantum information, we basically study the finite dimensional case. We consider a Hilbert space, and we are basically interested on the set of density matrices on the Hilbert space that represents the states of the system. And we introduce the notion of complete positive maps that are algebraically defined as maps which are n positive for every n. And the main map that are used in quantum information are the quantum channels, which are completely positive trace preserving maps from B of H into B of H dash for H and R are two Hilbert spaces. And these maps are characterized by being...
Sorry.
Yes.
Just a question in the previous slide. What do you mean by rho star? What means rho star?
Okay,
yes,
here it's a positive. Like rho star is the conjugate, the complex conjugate of the matrix rho.
Okay.
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 Okay. Here, these maps should be completely positive and trace preserving. We can also consider the dual to be completely positive, identity preserving, and they are well known as Markov operators. And here we have a very well known result that can decompose any completely positive map into a cross decomposition, satisfying this trace preservation condition. And for the quantum information flow, we have an input row, which is a density matrix. And when we apply it to the quantum channel, then we get an output state, which is a fire flow. This is the main operation that can be applied within a quantum, quantum information system. We have some properties of these maps, such as in the case of OCC, which are particular quantum channels, we have these maps are particular quantum channels defined through these set of density operators satisfying this condition, which are assisted by classical communication. And we have this property. They are satisfying what is called the data processing inequality. And it means that the complexity of the initial state is all the time bigger than the transformed state through the quantum channel phi. This applies also to the relative entropy and to many other entanglement measures, such as the negativity and the OA degree of entanglement. And here, what's really interesting is that we can see, for example, for the pure state entanglement, even the von Neumann entropy vanished. Therefore, this gives an intuition idea that the framework of the usual framework of probability is not sufficient to study these quantum system. And then often there are some sophisticated measure of entanglement that determine to which point the system is entangled and to which point the information are complicated to understand. Now, what we are interested in is the dynamics theorems. We can consider the quantum channel is said to be ergodic if it has only one fixed point. Equivalently, we have this ergodic average converge into rho star. So then we can show automatically that rho star is a fixed point, and within the finite dimensional framework, we have equivalence of these two properties. And there is another notion that is close to the ergodicity, which is mixing. Often people they make the confusion between them, but indeed they are distinct notions. Here we can see that the limiting quantum channel is given within this simplified form, and it's idempotence. So here phi hat of phi is equals phi hat. Also phi hat of phi hat is itself. And now for the mixing, we have the limit, the uniform, indeed, for any two given initial states, rho and sigma, the limit equals 0 of this quantity. And these two notions are different. Even we can find quantum channels which are ergodic but not mixing, but the converse, mixing implies ergodicity, but the converse is not true. A lot of works have been done in this direction. And what we are interested in is to define the ergodicity within the non-homogeneous framework, for which we lose a lot of interesting points, including the fixed point theory. Like we have a fixed point, we can consider the fixed point of the state itself. I mean, the quantum channel phi. But in the inhomogeneous case, we don't have this notion. So to build a clear idea, we go back to classical Markov chains. The inhomogeneous ergodicity for Markov chains have been studied by many authors, and we can see that a quantum chain which is inhomogeneous that presents time dependence transition from n to n plus 1. So it's defined through a sequence of inhomogeneous stochastic matrices, and then the transition from m to k within the interval of time, and k can be represented as the product of these matrices. Now, we distinguish two notions, which is the mixing, the weak mixing, ergodicity, weak ergodicity, and so on. Here we can see that these two notions of weak mixing and mixing are different. Through this example, we can see that the Markov chain with these transition matrices is weakly mixing, but it's not mixing. So based on this idea, we can define two directions of dynamics for the quantum inhomogeneous systems. Given a sequence of quantum channel phi n, we can compose the channels starting from phi naught till phi n, or the converse. Here we speak of the backward evolution, and here we speak of the forward evolution. Here we put the B to design backward, and F to design forward. And the application of these channels can be represented through the Krauss operators, which is here inhomogeneous. Like we cannot commute to Krauss operators here. Okay. Now we define the ergodicity notions here through considering the ergodic average at time n, which is defined the same way as the usual ergodic average, but here instead of considering phi to the power k, we have phi 0k to the t, which is like this composition in case where t equals f, the forward, and in the case where t equals b, we have this from 0 to n. Now we define the ergodicity of this sequence if there is an asymptotic, let's say asymptotic invariant state for which you have the limit. Here, what's really different with the homogeneous case is that rho infinity may not be even an invariant point for any one of them. And another additional point is that for the backward and the forward dynamics, the limiting point may be also different. And this is a very important point that shows to which point things are different to the usual homogeneous case. Then we define several notions of ergodicity and mixing. Here we can see that we can see here also we define uniform ergodicity, where the supremum converges independently of rho, and then also mixing if you have the limit. Okay, here it should not be phi bar, but phi 0n without bar. Okay, because it's the mixing, so we consider the sequence, not its ergodic average. And the uniform mixing here, it's right. If the limit of the supremum equals 0, and then the exponential mixing if this quantity decay exponentially. Okay, now we have this hierarchy of implication in the finite dimension scheme. We have the exponential mixing, the stronger one, it implies the uniform mixing. Then the mixing, here we have equivalence between uniform mixing and mixing, because you are within the finite dimensional framework. And also the uniform mixing implies uniform ergodicity, and also uniform ergodicity is equivalent to the ergodicity itself. The proof of this result is like somehow straightforward. The only non-trivial thing is to show this equivalence that requires like basic techniques. And now we go to the most important part, which concerns the weak inhomogeneous weak mixing for inhomogeneous quantum process, which is like the additional component to the notion of mixing and ergodicity. Because we speak of weak mixing, this notion doesn't exist in the case of the homogeneous dynamics. Okay, now we define the weak ergodicity using this notion, like the limit of this difference equals 0 regardless the initial states rho and sigma. And then also here the weak mixing defined through the same idea, but without considering the supremum. Also the exponential weak mixing, we have the exponential decay of this quantity. Now we characterize like the mixing in homogeneous case. Indeed, we show that in the backward dynamics, the weak mixing and the mixing are equivalent. And this due to the nesting condition, this nesting condition which is automatically satisfied in the backward dynamics. For the forward case, things are different, because often we have the mixing implies also the exponential mixing implies the weak exponential mixing. That's straightforward. But the converse requires this nesting condition. I mean, it's a sufficient condition. It's not okay. It may be sufficient, maybe, but this condition is crucial, and it implies that if we have this sequence is nested in this way, so using that deterministic compactness reason, we get the converse way. And we give this counterexample that shows that this nesting condition is necessary for the forward case. Here, as we can see, for the backward dynamics, we have the ergodicity in a direct way. I mean, for the mixing, it is equivalent to the weak mixing, but for the forward case, we can see that this sequence is weakly mixing, but not mixing, because as you can see, these sets are alternating between these two states, and then we don't have this nesting condition. But for the backward dynamics, it's determined by the initial state. It's equals to this pure state direct. So it's somehow stationary. Now we arrive to a nice result that shows that we can consider a characterization of weak mixing through considering a sequence, what's called here trajectory ergodicity. The trajectory ergodicity have been studied recently as an ergodicity in the quantum framework, but indeed here we show that it's equivalent to the weak mixing. And The same for the exponential weak mixing. We can show that this sequence is exponentially weak mixing if there exists a sequence Zn satisfying this inequality with mu is a constant between 0 and 1. And we have these three equivalents that characterize the weak mixing given a sequence Zn or for any sequence, and also we have this exponential weak mix. So it's somehow giving an element in this set, an element of this set for the nesting condition. We just choose an arbitrary element Zn from this set, this compact set. Then, due to the nesting, we get this characterization. Somehow, it's the sequential characterization of the weak mixing. Okay, now we can see that between homogeneous case and inhomogeneous case, we have a lot of differences. So we can imagine that the homogeneous case is just a section on this 3D like shapes. These 3D shapes here it's not that clear, but what I mean is that we have the external part is the weak mixing processes, and the red one is the set of weakly mixing quantum process. Here, the set of weakly ergodic. I mean, the black one here is the set of weakly ergodic. Here, the red one, the set of weakly mixing, and the blue one is the exponential weakly mixing processes. Here, we can see that we have this inclusion of these three sets. And given the section of the homogeneous process, we don't see this phenomenon of weak phenomena. We just see that here we have the set of ergodic in green, and then I mean in black we have the set of exponentially of ergodic process, homogeneous process, and in red we have the set of mixing process, and the blue one are the homogeneous exponential mixing. We have this inclusion, but indeed it's just section in a bigger set of processes, which are like characterized by the weak in the homogeneous case. I mean, in the homogeneous case. Okay, now we arrive to one of the most important results in this paper that concerns a Markov-Dobrushin mixing condition, which is based on a result that find a Markov-Dobrushin inequality for quantum channels. As you can see here, we have somehow a quantum analog of the Markov-Dobrushin inequality. Kappa phi is the infimum over the set of operators. If kappa phi is strictly positive, then we have the quantum channel phi is contractive. And it was shown in this paper by Dr. Luigi, Prof. Luigi, and Prof. Lu and myself. And it turns out that this Markov-Dobrushin inequality is also available to show the mixing in the weak case. Now, if we have a sequence of channel.
The question?
Yes, yes.
Can I ask a question? Can you go back to the definition of the Markov-Dobrushin coefficient? I'm not sure I got it.
Yeah, this one.
So here, this is so phi. So you take pure states psi, you apply phi to the channel, but then I'm not sure what is the inf of this phi.
Yeah, the infimum here is the essential infimum, defined this way. The infimum of a set of operators is the essential infimum, the supremum of elements B that are less or equal than every element in this family.
Okay, and then you take the trace of that, and this is what is okay. Because this is sometimes, I don't know how really, there's something called the contraction coefficient of a channel for the trace distance. So this looks like it, but it seems you need the stronger So like this k phi is like 1 minus trace of k phi will be always, I guess, bigger than the contraction coefficient, right? So for me, the contraction coefficient is just the supremum of phi of rho minus 5 sigma divided by phi minus sigma, like by how much the channel contracts the 3V.
I see that. I see that should be like because it's what you mentioned is like how to say a submultiplicative norm. So it's quite natural that we get that one less or equal. Yes, I agree.
Yeah.
But here, is there a way to determine the? I mean, if we want to compute the contraction coefficient, which is the optimum. I mean, is there like a way to compute it explicitly often? I know theoretically it's less than the Markov-Dobrushin, more precise. But what's really good in the Markov-Dobrushin constant is that we can compute it on the, as you see, on the right one projection.
Okay. Actually, we had the recent paper where we showed that the contraction coefficient is NP hard to compute. So in general, it is
NP hard.
complicated to
I see.
I don't know about that. Maybe this one is easier to compute. It's not clear how to do this infimum over the states, but maybe there is a formula in general.
Yeah, but here, as you see, are within the set of rank one projections. So I guess it's a good idea to see the complexity of the computation of this.
Yes, it could be, yes. Okay.
Thank you for nice question. Okay, so here we get this result that depends on the density of the contractive channels within the first n channels that we denote here by capital N of n. If we have like capital N of n channels that are contractive, we get for which we have the Markov-Dobrushin constant is strictly positive, then we get this inequality. And what is really interesting in this inequality is that we obtain different speed up of convergence. It can be exponential if this quantity is like big O of n, or I mean like equivalent to the constant times n, or also logarithmic. It depends on the density of the contractive channels within the first n channels, as you can see here. And this result is also available for both the backward and the forward dynamics. Regardless the direction here, once we have n contractions, I mean capital N contractions, we get the equality for both forward and backward dynamics. So I should put like a bit further. Okay, now we can see that we have this corollary in the periodic case. We can obtain the contraction decay.
Hello,
Hello,
Dr.
is my
Abdessatar.
voice
Yes.
clear?
Yes, clear. Yes. Now
Okay.
it's clear, but before no.
Good. Okay, now I said here we can also find the speed of the convergence in this periodic case. Now we arrive to one of the most important applications of these results to the inhomogeneous. I mean, the non-traditional invariant, like many states are very important states in many-body physics in the one-dimensional. They are the paradigmatic example of one-dimensional many-body systems. And hello, is my voice clear?
Yes. We hear you.
Good. Okay. Here we define a quantum channel associated with the state that that's defined through this sequence of tensor that are defining automatically a quantum channel phi n. And we define the backward and the forward dynamics, and then we can see that how to say, within this algebraic framework of quasi-local algebra, I don't know. Do you hear me?
Yes, Dr. Abdessatar. Yes, we hear you. Yes.
Good. So here we define this state on this quasi-local algebra of observation. And using this embedding, of course, you can see the algebra U1 to N as a subalgebra of U1 N plus 1. And then we see that using this translation, sigma, we can shift the process into the position from 1 to N plus 1. Then we define this state. We are interested in the state defined by the expectation value of x given the state psi. And we see that this state can be computed using the quantum channel. Using these results, we find the limiting state. Find the limiting states based on these results. Like here, I can see that it's not complete, but using this composition of channels, we find the limiting distribution phi that shows that how to say, like is my voice clear?
Yes.
Okay, I will show you like the result here, because has to use the quantum channel approach to find the limiting distribution of the sequence of states. And we characterize it using the invariant, I mean the asymptotic invariant state that's given by the contraction here. I mean for the mixing case, because it's not written in these slides. Excuse me, I will show you here in the paper. Dr. Rafiq, is my screen clear?
Yes, the paper now.
Okay.
No?
This one is the application to the here. Here we start the application to the matrix product state, and then we define this limiting state. Then we obtain this result. If the infimum of the Markov-Dobrushin constant is strictly positive, then we get this limiting state defined on the infinite product algebra, which can be defined through the asymptotic invariant state in this way. This is the result that somehow that investigate the matrix product state in the Heisenberg picture by considering this state as a limiting state. And also in another related work, we showed that these matrix product states in many cases they are observation, as here in this work, show that many of these matrix product states are observation of hidden Markov model. And then this result is I think it's really promising given the importance of hidden Markov model within the quantum information framework. And here we show that in this paper we show that these matrix product states, for many of them we have this, we can represent them as observation of hidden Markov model. Combining these two results, I think like we can have more fruitful results regarding the information flow of these processes. I think I will stop here. So thank you very much. I'm so sorry for these connectivity issues, and questions are welcome. Thank you.
Thank you, Dr. Abdessatar, for this nice talk in a nice topic. Are there some questions, please? So I start this session of a question by a general question. Given that this webinar focuses in applied mathematics, what do you see as the most immediate application of your framework in current quantum computing or quantum error correction protocols?
I see. Thank you for this nice question. Indeed, like quantum computing is like a new field in which we can see a lot of development. And I don't know how is it exactly how people see it. Like because there is a big difference between having a hardware side of quantum computing that requires a lot of silicon, as you know, like one digital qubit requires around 1,000. For now, what's the state is that you have only the NISQ framework. We have some like devices with a certain number of qubits. But for what's really interesting and promising regarding my work, or also all the works that are in this direction, quantum information, I think they are much more important than developing like the hardware side for now, because it's still long to find like a well-established quantum computing from the hardware side. But from the algorithmic side, as you know, that the quantum computing idea starts with algorithm, starts with the idea of Feynman, who said that like there are some algorithms that requires exponentially faster, and then they develop the first development through the Shor algorithm, the Grover algorithm. All of them, they are mathematical algorithms, but they require like exponential faster computer. Therefore, I think like this framework can be how to say, as most of the groups do, they take their works and somehow they like translate them into quantum circuits and then a related algorithm. But in all cases, what I really believe is that since the classical Hedda-Markov model and the related model play a crucial role in classical machine learning, and given the NISQ framework, which are hybrid mode, classical and quantum, I think it's quite important to develop like quantum algorithm based on quantum Hedda-Markov models. I mean, namely the ones that are developed in infinite product algebra, because they are the natural extension. Because given the diagonal subalgebra, the maximal diagonal one, you get exactly the classical Hedda-Markov model. Therefore, you have that bridge between classical and quantum that allows you to take algorithm from the classical to the quantum and vice versa. That's what I think. If maybe some of the audience have compliment on that, maybe it will be helpful for us.
Okay, thank you. Thank you. We have. Sorry. Yes.
If I.
Omar.
Yes. So it's still theoretical work, but I had recently some work on. It's in this homogeneous case. It's in trying to compute the capacities of these. So I see this the sequence of channels as the noise model. So I imagine that my hardware, for example, has these phis as the noise, and I think of the phi as the noise per unit time. And I look at large time, what is the capacity of such channels in like storing quantum information? It's still a theoretical question, but correction. So yeah, we studied a bit. So I see this as related work as what you did, maybe to do this for inhomogeneous in the inhomogeneous setting, and say what would be the properties that allow you to determine the capacity. So I can send you the rest. you would like.
I see. I think I have seen some of your works, recent works, 2025, and I
Yes,
had like
it's
one
quite
question. I was
recent.
about sending you this question, but I'm really happy to see you. Like about the randomness that you put, or like on the channel, the classical randomness. Like I see that they are considering somehow random matrix product states and random quantum channels.
I wasn't referring, maybe this
Maybe
is
some of
different
your
work,
co-authors
but
involved like
the,
random quantum channel.
yes, I think this is maybe, I think this is more work, or Cecilia L'Ancien. Here, maybe I can put, I don't know, I put it in the chat or something, the relevant paper. It's also a recent paper, but so it's called
You can share the paper, Fawzi,
yes,
Omar.
yes.
Please, Abdessatar, can you stop your chair?
Okay, I will stop sharing right now.
Okay.
Or maybe uh,
I think I stopped sharing, yeah?
No.
I meant,
Okay.
maybe it's simpler
Not yet.
that I put it like this. This is the link for the paper I was referring to. There's also other, I mean, here I refer to my paper, but this started a bit like this way of looking at it started by a paper by Nilanjana Datta and her group, if you have heard of her. It's definitely cited here. So I think, so here what we do is we characterize the capacity of such like a process in terms of the peripheral spectrum, right? Some properties of the peripheral spectrum. You know that this it's close to an algebra, and so it depends on some properties of this algebra. So I think this could be interesting.
I see. I found the paper, and
Yeah, excellent.
I think
Okay, yeah.
in homogeneous, I think it can be done, like in the in homogeneous case.
Sounds good. Yeah. Actually, if I can mention also, just this is more on the related work side. I think there is people who looked at quantum something called the quantum Dublin coefficient. And I think it's related to this Markov-Dobrushin, but I don't know the exact details. But so maybe I give you the link. You might
The
find it
quantum
interesting or
ergodicity
not. I don't
coefficient,
know.
yeah?
So it's
Do you mean the
it's
quantum
called
ergodicity
quantum Dublin
coefficient?
coefficient.
Dublin.
Sorry, it's
The
called
quantum Dublin or
the
the
quantum
quantum
Dublin
ergodicity?
coefficient.
Mhm.
Yeah, I'm not an expert in this, so I don't know exactly, but I think it's related to it's also an upper bound on this, what I call the contraction coefficient. So and what you presented, this 1 minus kappa is also an upper bound, and so I don't know how these two are related. Maybe it's the same actually, but maybe the Markov-Dobrushin is the same as, or it's a different quantum
I mean,
generalization of
I
the
have seen a
classical
recent paper
distribution,
on
so
that
it
in
could be worse.
2025. Am I right?
Yes, it's exactly. I put the link. It's maybe
I
this
think
that
it's
you.
the same
It's
because
called quantum
in
Dublin
that paper
coefficient.
they
It's a
considered
good study.
the time continuous, but I think it's exactly the same.
Ah,
It's exactly the same contraction.
okay.
Like I don't know how even what's new even like because
Oh,
it's exactly the same Dobrushin.
okay.
I see that maybe
Yeah,
yes,
it might be,
but
yes. It might be good to connect because they might not know the different areas that are coming more from the mathematical part. So yeah, it might be useful for. I mean, they found some applications in quantum information. I think actually it's a super long paper where they introduced in like many variants of this quantum Dublin coefficients and give various applications. So yeah, it could be interesting.
it's a really good opportunity to maybe ask you some questions, even like because maybe we don't have in about like do you think that quantum information that people are developing now they are useful for related to what Dr. Rafiq asked on quantum computing? Like as you see, it becomes a big trend. People are working on quantum computing, like expert and non-expert, and you see.
Yes. I mean, of course, as all areas, there is things that go from the more like the hardware people to theoretical questions, and so yeah, but I think there are theoretical questions that are like of relevance for trying to improve how we do the hardware. And I think actually in particular this question, these questions in this paper, so we didn't get the chance to I mean, we have some examples here. In this paper, if you look at, we have some examples where we discussed some of the hardware that is used. Some of the hardware is called cat qubits, but you can think of it exactly in this way, like, and I think we describe it. We describe it a bit later, that how to think of these cat qubits in this way. And so, yeah, we couldn't prove stuff that is directly useful for these cat qubits. But I think if one pushes this a little bit more and studies it in a more general framework and tries to find optimal encoding and decodings, it could potentially have impact there. To study the question from an abstract mathematical point of view, because usually it's mostly physicists who study this, and so they model the physics, and so they don't try necessarily to optimize the full framework. So I think there could be some interesting things to do here.
I see. When it comes to mathematical framework, I think like maybe a good framework to study this is quantum Markov chains. As you know, we are one of the people who developed quantum Markov chains, like from the quantum information viewpoint. But you know that originally it was being like introduced as a non-commutative extension, of intense product algebra by Accardi in his 19th century. But then you see, before even his work, there were some works by some other Russian mathematician. He's Italian, but he did his PhD in Russia. And then you can see that there were a notion of Markov operator, which is exactly the dual through the Hilbert-Schmid operation of quantum channels, what you see now. How quantum channels are very famous, but Markov operators, they are somehow, how to say, the quantum information people, they are somehow like, how to say, developing things in a fast way, so that the theoretical approach, it becomes somehow not that investigated in like recent years.
Some other questions? I have a general question for both of you, Dr. Abdessatar and Omar. What will the next generation of computing look like?
Maybe next generation, actually, I see a lot of things about, but maybe I let Dr. Omar if he has something in the direction.
So yeah, it's difficult to say. So first, we're not sure, right, that we'll have quantum computers. So it's now I'm just guessing, but the guess is that if it's growing like this, is that we will have like very like specialized quantum computers, and a few of them, but they will be sort of supported by very large classical computers, right, to sort of operate and like, so for example, I mean, so in order to operate a quantum computer, you actually need a lot of classical computations, right? So for example, for error correction and things like this, so just you imagine this box, which is the quantum computer, you actually need to do a lot of algorithms to just run this quantum computer. So the way I mean, if you ask the future of computing, I mean, we'll of course still have classical computers, and we might have these hybrid devices where with very large classical computers and together with also a quantum computer. And the hope is that, like, by using the best of classical computation together with quantum computing, this will allow us to solve some tasks faster.
Okay, thank you. Other questions, please?
Okay. Yes, Dr. Rafiq.
Yes.
Yes, I wanted to say some words. Even I shared with Dr. Souissi many discussion, we shared a long time joint works. So before to go to at least one question, I wanted to say some general comment maybe for the people here who some of them are not specialists. So my first comment is about the time in a homogeneous quantum dynamics. So the main point here is the fact that the focus on sequencing quantum channel rather than a single fixed channel reflect realistic quantum system. Because if we take every one fixed channel, in fact, in real model from real life, in general, we have a sequence and not a single one as a mathematical model. And then this subjected to maybe a different research line, like control, like noise, as indicated by Dr. Omar, or environmental drift in some recent works. And other remarks distinguishing forward and backward dynamics is in fact mathematically non-trivial. And in physics, it's very meaningful, especially since quantum channels are generally non-invertible. So from the absence of invertibility, so we have like an essence to make the distinction between forward and backward. And I think in the talk, there is at least a result where there is we see this difference, because in some direction we have concretization of the phenomena unlikely to the other one. So in my opinion, this perspective pushes quantum ergodic theory beyond the, I can say, the usual or repeated interaction framework, and it can align as well with the modern quantum control and open system modeling. And maybe, Souissi didn't indicate it, we have recent work in this direction with open system modeling. My second general comment is about quantum Markov-Dobrushin approach. So here, importing Dobrushin type contraction coefficient into the quantum setting, in fact, is a strong conceptual contribution. The emphasis on explicit convergence criteria and exponential stability makes the framework operational rather than purely qualitative. So this approach provides a bridge between classical non-homogeneous Markov chains, quantum channel theory, and operator algebra ergodic theory. And then the bridge between these different research line is significant. So in this line, I think this framework has the potential to become like a standard tool for analyzing stability and mixing in non-stationary quantum evolution. And this is similar to how spectral gaps are used to in the case of homogeneous, in the homogeneous case. The last point in the talk is about non-translation invariant matrix product state. So extending mixing result in this case is particularly valuable. Why? Because a real system rarely satisfies strictly homogeneity, in fact. And then we go back to my first remark that taking this sequence and the connection between extending this mixing result to non-translation invariant matrix product state is, in fact, this is the point to be able to model real phenomena or phenomena coming from real life in different direction. And disconnect abstract ergodic result to tensor network theory. I think we started just to discuss in this direction, and Dr. Omar and maybe Dr. Rafiq asked about this direction and the trend of quantum information and the quantum computer. This is in fact central in both condensated matter physics, at least in the in the theoretical part, I attended some lecture in the last period given by people from quantum theoretical physics, and then they indicated that in fact they need this extension of mixing in this strictly non-homogeneity. So this is a general comment about the topics in the talk. But maybe it will be interesting if I have, Dr. Rafiq, I have 1 minute to ask a question.
Yes. Sure.
So about uniqueness of a stationary state, for example. So Dr. Souissi, and what minimal assumption, Dr. Souissi, is there? Or,
yes, I can hear you.
So, and what minimal assumption does the framework guarantees uniqueness of asymptotic states in the time inhomogeneous case? What is the minimal assumption?
Actually, you know, in mathematics, often minimal assumptions are really hard to find. But as you can see here, I just gave some sufficient condition, like for the forward direction, that nesting condition is sufficient. But it's not necessary. We may have some mixing with no like we are not sure. I'm not sure. But even maybe also these definitions become even more sophisticated when we go to the infinite framework of von Neumann algebras. There, even that notions that are equivalent in the finite dimension concept become completely different. And the difficulty when we try to find the counterexample, why we have this property and not this property. As you remember, Dr. Barhoumi in our last paper, they asked for that counterexample for which we can have mixing, but we don't have, I think in this paper, they asked for a counterexample for which we can have mixing without having Markov-Dobrushin contraction. And it was quite hard to find such a counterexample. And this one was in the homogeneous case, just to give an idea to which point these things are hard to find from a mathematical viewpoint. Like I think this counterexample, this one, in which we find that the Markov-Dobrushin constant is 0, but the channel is mixing. How if we ask the same question in homogeneous case, it becomes much harder, like finding some counterexample, and even worse again if we go to the infinite dimensional case, for which the equivalence is not guaranteed between all the notions that are introduced of ergodicity and mixing here. Therefore, it becomes really challenging, like to extend this framework into the abstract algebraic language. I mean, even defining, I don't know whether there is a well-established theory of weak ergodicity and mixing even in the von Neumann framework. I don't know about that, but it should be like good to extend. It requires a lot of like hard mathematical tools, but it's really good to extend it in the algebraic operator language.
Okay, so I understand that the optimality of a criteria, in fact, is not sharp. It's just sufficient condition.
Yes, here we just give some sufficient condition for to get the results. As you can see here, we get the equation 20. It gives sufficient condition. And what's really important is that this sufficient condition allows us to find this sequential characterization of mixing, and this sequential characterization coincide with this work, coincide with the results given in this work, which was also applied in this work by these two famous American mathematicians. One of them, maybe Dr. Aber knows some of them. One of them in, I think, in IBM Google, and the second in the Michigan State University. And here they get the result using an ergodicity condition based on the classical Markov chain, the classical like probability measure. They involve the classical randomness here to be able to find an ergodicity condition based on which we can find the weak mixing. What is here considered as a sequential weak mixing, and they mentioned it as ergodicity there. And it means that one of the directions that is really good to investigate is to see whether this deterministic approach that we gave here, I mean, the nesting condition that we gave, is it equivalent to the reducibility condition that was investigated here in this work?
Okay. I think that Dr. Diko has a question. Dr. Diko? Yes.
Yes, Dr.
Yes, please. We don't hear you, Dr. Diko. Okay.
Okay, Doctor. Maybe I can just add this comment. I can also go back to the comment of Dr. Omar about connection of this research line with the quantum information theoretical application, at least not maybe in direct application, but theoretical aspect of quantum information. Then, for example, relating the mixing rate to the study of the application for quantum error correlation and the fault tolerance in time-dependent noise model, I think is not very far from our development. Then we can try to do some attempt to give more concrete mathematical connection between this theoretical mathematical result and results coming from people working in quantum information, at least in the theoretical application.
Yes, exactly. Yes. I think this a lot of things can be done in this direction, both from a theoretical viewpoint and like also applications to quantum information.
Yeah.
Okay. Thank you, Dr. Abdessatar Barhoumi, for your questions and comments. Dr. Diko, can you ask your question, please? Okay. If not, we have to thanks again, Dr. Abdessatar Souissi, for this nice talk. And see you after 2 weeks, 6th January, for the next talk. Thank you.
Thank you. Thank you very much.
Thank you, everyone. Thank you.